Math teacher should. All right. Good afternoon, lads and ladies. Welcome back to MAC 1140 Pre-Calculus. Today is our second day of class, and I'm excited to share more with you today about functions. We're going to talk about solving inequalities, which is a big deal. Technically, it's a kind of review thing, but I have a feeling that most of us have either never seen it, or if you saw it, it was maybe in passing. And then we're going to move on to chapter 2 stuff. We're going to talk more about graphs of functions. We're going to talk about how to get certain kinds of information from the graphs of functions, definitions of mins, maxes, increasing, decreasing, all of that good stuff. So without any further ado, let's roll into it. Of course, this is MAC 1140, pre-calc. It's a lecture. Put this out of the way. Today is the 29th. Today. I want to go into more detail about domains. Specifically here, we're going to talk about inequalities needed to find domains. We're going to talk about net change and average rates of change. And then we're going to begin section, this is all 2.1 stuff. We're going to then jump to 2.2. On info from the graph of a function. Specific things here include like mins and maxes, increasing, decreasing, etc. All right, so that's our plan for today. I want to remind you, you have homework in WebAssign right now. It's been up since yesterday morning. Normally that would be due tomorrow, right? Normally the Monday homework is due on Wednesday. The homework for that week, the first two days, due the following, due the Wednesday after that. Of course, because this is the very first week and I want to give you guys time to ramp up and get used to this shit, because there are some people who maybe are here for the first time today. I didn't want to do that to you this week, but just a reminder, the way our homework scheme works, right? You have 2 homeworks due every week, one on Monday, one on Wednesday, and normally the homework that I open for you on Monday would be due on that Wednesday. So you just really need to stay on top of that stuff. If you're not in WebAssign yet, you need to get in there now. Reminder that you don't need the access code. Right? You do not need to have your access code in hand to go ahead and register for our class in WebAssign. You can use the temporary or trial access until your code gets here. All you need is the class key from the syllabus. And in case anybody, again, is here for the first time today, our syllabus, the full syllabus, you can download it from this link here in Canvas. This is the home page for our Canvas class. You click this link and up she'll pop. Looks like this. Class key you need for WebAssign is here. If you're having any trouble getting into WebAssign or getting things to do what you need them to do, just come see me in an office hour, send me a message in Canvas or an email. Any of those are fine. I do have an office hour this afternoon from 3 to 4, as I will have every class day. All right, so last time we talked about functions, we talked about function notation, we talked about finding domains and ranges a little bit. The range of a function can be pretty tough to figure out unless you have the graph, but the domain of a function, I gave you some tools to find. We said you want to watch out for red flags, right? A domain red flag for a function could be any variable stuff downstairs in a fraction, or any variable stuff underneath an even root, like a square root or a fourth root. the latter category of domain red flags, so we'll begin here, recall, to find the domain of a function, look for what we call domain red flags. And a red flag here is what it sounds like in other contexts. It's something that should set off alarm bells in your head. The two big domain red flags that we have at this point in the class are variables downstairs in a fraction. We know that you can't ever divide by 0. So if you have some variable quantities in the denominator of a fraction, then you need to make sure that that stuff isn't 0. Or in other words, to find the domain, you figure out what values of that variable would make the bottom 0, and you kick those out. The other big red flag is variables under an even root. And we discussed both of these in some detail yesterday. If you missed yesterday's lecture, please rewatch it, take notes. But I want to go into more depth today. Specifically, I want to look at the second red flag and how we can manage that. The reason that a variable under an even root or a variable quantity under an even root is considered a red flag is because you cannot take an even root of a negative number. So if you have some variable stuff under an even root, you need to ensure that that stuff is positive. The way you do that is by figuring out what values of the variable would make that stuff negative and then kicking those out of the domain. I see there's some questions in chat. So for this week's homework, is it combined, or is the number on this week's homework comparable to Monday and Wednesday's homework? So I think the question is coming from the natural place. This week's homework set is massive, right? It's very, very long. The homeworks will vary in their length, but this is about, I'd say it's a little bit bigger. It's about 2/3 larger than a traditional 2-day homework set would be, because we've got the extra time, and because this week we're actually covering quite a bit of material very fast. A lot of what we're covering this week is stuff that's technically covered in college algebra, so we have to go through 5-6 sections a week, and this first week is one where it makes sense to knock out a bunch of the kind of early prerequisite stuff. So I think there's 75 questions in this week's homework set. I would say you can expect each homework set to be somewhere between 30 and 50 questions. So this is larger than a typical homework set will be. 75? 73.
I have a question.
Yes.
Hello?
Or Jada, go ahead.
Yeah, so like I was doing a little bit of the homework, and like you have to submit it like one by one. Like how do you submit them all, like all the ones you've done so far?
Good question. Yeah, so I recommend submitting, like, do a problem, submit the problem. But my understanding is that WebAssign will save your work even if you haven't like submitted the page. So if you're nervous about things not saving, or you're nervous about questions you haven't like about submitting the whole assignment, I think you should be okay. And I'm wondering if anybody else can verify that for me, because I don't see it from the student side.
You should be okay. It does save automatically.
Yeah, it saves it.
Okay.
Yeah, that's
Because
what
I was like, do I have to keep clicking submit for each question? I'm like, it's wasting a little bit on my time.
Yeah, you do have to individually submit it, but it does save it.
Oh, so we have to submit each question? We can't submit them all at the same time? Okay.
I don't believe. Yeah, I do believe you have to submit each question, but it should save your work. If you don't submit, it's not the case that should go away, but you'll still need to submit. So I recommend solve a question, submit it. Solve a question, submit it, and go on like that. All right. So let's go ahead and continue looking at the domain stuff, specifically the variables under an even root thing. To give you an idea of what we're talking about, I want to just show you a little example. I might like to find the domain of the function f of x equals the square root of 9 minus x squared. So we look at the function, we ask, are there any red flags? Are there any variables downstairs in a fraction? No, well, there's no fractions here. Are there any variables underneath an even root? Yes, yes, there are, right? The square root is an even root. So we've got the variable quantity 9 minus x squared underneath that even root. So that is a red flag. The thing to do is to ensure the stuff under the radical is positive, right? Or not negative. 0 is okay, but negative under a square root is not okay, right? That would give me a non-real complex number. So we have to, we must solve the inequality nine minus x squared is greater than or equal to 0. Right? I need to make sure that the stuff under the radical is greater than or equal to 0, is not negative. Could I see just by a show of hands, how many in a previous math class have been told how to solve inequalities like this? It's called a nonlinear inequality. Yeah, you can raise your hand physically on the screen, or you can use the hand raise response in Zoom. I'm just curious. Okay. A handful of us, but not a majority. So the trick to solving an inequality like this, a nonlinear inequality, is to make what's called a sign chart. We're going to see how to do it for this particular one. And then I'll discuss how it's done in general. This is in your textbook. It's in one of the preliminary sections, section 1.8. So if you want to read the textbook's detailed stuff, I encourage you to do that. Feel free to check it out. Here's what you do. So 9 minus x squared is greater than or equal to 0 is logically equivalent to, or the same thing as, I can factor this. That's 3 minus x times 3 plus x is greater than or equal to 0. The thing is, you can't just like add the x squared over and take square roots. That works great for equations, does not work for inequalities. So instead, we have everything on one side of the inequality. That's already the case here, right? We have a 0 on the right and everything else on the left. Then you factor this thing to figure out where it's capable of changing sign. 9 minus x squared factors as a difference of squares as 3 minus x times 3 plus x. And then the two places where these factors are 0, 3 minus x is equal to 0. When 3 is equal to x, or x is equal to 3, and 3 plus x is equal to 0 when x is equal to negative 3. Pull everything to one side, factor, and then draw a number line. On that number line, you will put the two numbers that make this thing equal to 0. Right? So we factor to find out where this thing is equal to 0, and then we put those on the number line. So here's my number line. And you'll notice that this splits the number line into 3 regions. from each of those regions, you will grab a test point. You will plug that test point into either this inequality or this one. Doesn't matter because they're equivalent. Usually they just say plug it into the original, but really doesn't matter. So over here on the left, I'm going to test x equals -4. In here, I'm going to test x equals 0. And over here, I'm going to test x equals +4. If I plug -4 into this inequality, I get 9 minus -4 squared is greater than or equal to 0. -4 squared is +16. So this says 9 minus 16 is greater than or equal to 0. And 9 minus 16, that's a negative number, right? What is that? That's a -7. -7 is greater than or equal to 0. And that's not a true statement. So we can cross this region off. When I test x equals 0, I get 9 minus 0 squared is greater than or equal to 0. Since 0 squared is 0, this is the same as saying 9 is greater than or equal to 0, and that is a true statement. So I'm going to put a little check mark here. And if I test +4 in the far right region, I get 9 minus +4 squared is greater than or equal to 0. Well, +4 squared is the same as -4 squared. This is again 9 minus 16 is greater than or equal to 0, which is -7 is greater than or equal to 0. And that's not true, so I cross this region. The solution to this inequality is the region or regions with the check marks. There are other notations for these charts. Some people like to test one factor at a time. There's a handful of other ways to do it. I invite you to take a look at the book if you don't like this one, or Google. There's lots of good YouTube videos out there. But this is how I encourage you to do it, especially when you're first getting used to this stuff. So the solution to our inequality, 9 minus x squared is greater than or equal to 0, is the interval from -3 to 3. And we have to figure out whether to use the closed bracket or the open parentheses. You do that by asking whether the endpoint itself solves the inequality. So if you plug 3 in here, you get 9 minus 3 squared is 9 minus 9. You get 0 is greater than or equal to 0. That's a true statement. So I can include the +3. And similarly, if you plug -3 into this inequality, again, you get 9 minus 9 is greater than or equal to 0, so I can include this guy. So the domain of f of x equals the square root of 9 minus x squared is the closed interval from -3 to 3. That's it. It's not too bad. It's possible to have problems where you've got multiple red flags and you handle those the way you think you would. You do them one at a time, and then you just take the stuff that satisfies all the requirements. Any questions on the example here?
I have a question.
Bianca, yes.
So when at the first step, when you went from, did you factor?
Yes.
Was that the first step that was factoring?
Yeah, from here to here, I factored.
Okay, okay, perfect.
And the factoring rule I'm using there is called the difference of squares. A squared minus b squared can always be factored as a minus b times a plus b. So 9 minus x squared is a difference of squares. That's 3 squared minus x squared. So I can factor that using this difference of squares rule. All right. Let's take a look at one more domain problem, and then we'll move on to the next order of business. All right, here I would like to find the domain of the function g of t equals the square root of 2t minus 1 divided by 2t plus 1. I see there's another question in chat, so after giving a second for people to write this down, I'm going to go back and address Jalen's question there in chat. We tested x equals 4 the same way we tested -4 and 0, by plugging that x value into the original inequality and checking to see whether we got a true statement, Jalen. So coming back here just very quickly. For the right region over here, I chose to test x equals 4. And I tested that by taking x equals 4 and plugging it into the original inequality. So that got me 9 minus 4 squared is greater than or equal to 0. And that simplified to -7 is greater than or equal to 0, which is not a true statement. So I need to cross out that region. Here I have 2 red flags. I do indeed have some variable stuff downstairs in a fraction. And I've got some variable stuff underneath an even root. So we've got both issues here. So I've got 2t plus 1 downstairs, that's a red flag. And I've got 2t minus 1 under an even root. Both of those are potential problems. First, let's take care of this. I know I'm not allowed to divide by 0, right? Division by 0 is not an allowed operation. So I need to make sure that 2t plus 1 is not equal to 0, because that's downstairs in my fraction. If I were to plug in whatever value makes that 0, the function would be trying to divide by 0, which is no bueno. So to deal with this, I'm going to figure out when 2t plus 1 is equal to 0. I'll do that by just solving for t here. That gives me 2t equals -1. And that gives me then t equals -1/2. All right. So t is not allowed to be equal to -1/2. Right? T equals -1/2 can't be in my domain because it will make the function undefined. Making sense? Ooh. All right. Big thunderstorm just came through my house, and it sounded like we got a little brownout there. So if you lose me, if my power goes out for a second, stay. Don't leave. I'll be back. It'll probably come right back. If power goes out and I'm gone for more than 15 minutes, you guys are welcome to bounce. But please, if it goes out for just a second, be patient. Okay. The other thing we had here is 2t minus 1 under an even root. So I need to make sure that 2t minus 1 is greater than or equal to 0. This is not a nonlinear inequality. The last inequality was nonlinear, so we had to use a sign chart to solve it. This is a linear inequality because 2t minus 1 is a linear function, right? The graph of this would be a straight line. So we can solve this guy just using kind of regular algebra without thinking too hard. I can add 1 to both sides of this inequality. That gives me 2t is greater than or equal to 1. And then I can divide both sides by 2. Getting the t is greater than or equal to 1/2. Okay. So in order for a t value to be in my domain, that t value needs to not be negative 1/2, and it needs to be bigger than or equal to positive 1/2. So it can be useful to draw a number line. 0 here, 1/2 here, negative 1/2 here. I know I need my t values to be bigger than or equal to positive 1/2. That's this stuff. And I know I can't have this guy in here. He needs to be out. But it turns out this doesn't even matter, right? In order for the second requirement to be happy, the first requirement's automatically happy. This will never be equal to 0 if t is greater than or equal to 1/2. So my domain here the closed ray, positive 1/2 to infinity. It's this set. All right. Any questions on this or the last domain example?
We only use equality when we with the radical.
Correct. Yeah, the radical, we know we need the stuff under the radical to be greater than or equal to 0. So when we're talking about domains, that's the only place we need an inequality. That's correct. Any other questions? Alrighty then.
I have, oh,
Oh,
sorry.
yeah, sorry, no, go ahead.
With the domain, wouldn't it be all numbers except like 1/2? Like, could it be less than 1/2? Or does it have to stop right there?
Has to stop here. I can't take anything to the left of 1/2 because that would make 2t minus 1 negative. For example, try plugging 0 in. If we ask what is g of 0, the top would be the square root of negative 1, right? And we can't take a square root of a negative number.
Yeah.
So that's the issue there. So these kind of inequalities lead to intervals, and kind of this restriction leads to us punching out individual numbers. So if you've got some variable stuff downstairs, you can expect to remove 1 or 2 numbers from your domain. If you've got some variable stuff under a radical, you can expect to remove entire intervals from your domain.
Okay. Thank you.
Of course, of course. Any other questions or comments on this guy before we move on?
In the domain, can you read the
Oh, Erica, you sound kind of cut in and out on me again. Could you repeat the question?
in the domain, it's a parenthesis and a bracket on one side. Can you explain that again?
Yeah, so it's a closed bracket over here and an open paren over here. So 1/2 itself is allowed, right? Really, this set right here, this interval, the left closed, right open interval from 1/2 to infinity, is the interval form of this inequality. So we're saying here t has to be greater than or equal to 1/2. And that's why I drew it down here on the number line. So what are all the numbers that are greater than or equal to 1/2? Well, it's 1/2 itself and everything bigger than 1/2. So the bracket is our way of saying this number is included in the set. That's what the bracket means. And so we're saying here this interval is the left closed, meaning the left endpoint is included, interval from 1/2 all the way up to infinity. So we're going to take 1/2 and anything bigger than 1/2. That's what the interval notation here means. If we want to revisit interval notation, the open interval from A to B, this is all numbers x satisfying A is strictly less than x is strictly less than B. And on a number line, it's just the stuff that's between A and B, not including A or B themselves. The closed interval from A to B, this is all numbers x satisfying A is less than or equal to x is less than or equal to B. And on a number line, that looks like this. It's everything from the open interval together with the endpoints. And then you can mix and match those as you want. You can have left closed, right open. So the left endpoint would be included and the right endpoint wouldn't be. You could have left open, right closed. So the left endpoint isn't included, but the right endpoint is. And then the infinity symbol, we always use open parens with the infinity symbol, because infinity isn't technically a number, it's not a real number. We cannot get to infinity, so it wouldn't make sense to say I'm going to include infinity. If this is something you're rusty on, which is totally understandable, especially if it's been a little while since you've looked at it, this is another thing that's covered in the preliminaries chapter of the textbook, back in chapter 1. It might be worthwhile to take a look at some exercises from, I think, probably 1.1. Yeah, section 1.1 is where they talk about real numbers and interval notation. Or you can come by office hours. Be happy to look at some of those with you in office hours. Any other questions on this one? Okay. So the next thing I wanted to talk with you guys about is net change. Sure, yeah, marination is good. I said net change is the last little topic in section 2.1, I believe. I don't think we actually get to average rates of change in there. But we do talk about net change. So definition. The net change in a function f from x equals a to x equals b is, by definition, f of b minus f of a. So the term we're defining here is net change. In terms of the graph, we're asking how far did the function travel up or down over an interval? So sort of the picture here. I have some function, maybe looking something like this. It's the graph of f of x. And I have an interval from a to b. The net change is the vertical distance between these 2 points. The point right here is a comma f of a. The point right here is b comma f of b. So if you subtract those y values, f of b minus f of a, that'll tell you the height. This is the net change in f of x from x equals a to x equals b, which is f of b. So I think, how much did the function change? The output from the function. As x goes from a to b, how much did the function grow or shrink overall? Net change is not terribly useful, if I'm honest, but it is a building block for something called average rates of change, which are very useful and very important down the road. And we can take a look at just playing around with the function notation and getting comfortable finding the values. So let's take one here from the textbook. Let's find the net change for f of x equals 1 minus x squared from x equals -2 to x equals +5. We know the formula for net change. It's f of b minus f of a. A is always the smaller number. B is always the larger number. So here this is a. And here this is b. So the desired net change here is f of 5 minus f of -2. And of course, I need to know what is f of 5 and what is f of -2. F of 5 is 1 minus 5 squared, which is 1 minus 25, which is -24. And f of -2 is 1 minus -2 squared, which is 1 minus 4, which is -3. So I can plug those guys in here. F of 5 is -24 minus, that minus is this minus. F of -2 is -3, and I'll put this in parentheses here because I want to be careful with my minus signs and make sure I'm understanding what's going on. So that's -24 minus -3, which is -24 plus 3. Right? Subtracting a negative is the same as adding the positive. And if you add 3 to -24, that brings you back in the positive direction towards -21. So the net change for this function from x equals -2 to x equals +5 is -21. And that means if you were to look at the graph, from -2 to +5, this function overall goes down 21 steps.
I have a question.
Sure.
So with the A and B, do you choose the A and B on which number is the biggest?
A is
Since B
always,
is first.
yes, yep, yeah, A is always the smaller one.
Okay, cool beans.
Cool. Associated with this concept of net change is something called a difference quotient. And these appear in your homework. They're really good practice with function notation. So I want to work one or two difference quotient problems with you as well. Last call for questions on this. This is the only example I'm going to do with net change since it's fairly simple. Okay. All right. So you remember from yesterday, I said that function notation is one of those super important things. It's one of the main things we need you guys to get comfortable with so you can do well in calculus. These problems where you're asked to find and simplify the difference quotient are sort of the perfect problems for that. Because you need to figure out what f of a plus h is, and then put that into this formula with the other less complicated pieces, and then do some algebra to simplify. They're really great problems, and I'll tell you right now, one of these shows up on my test for this class every time. So let's begin. If my function f of x is 1 over x plus 1, then f of a is going to be 1 over a plus 1. All right, we're just plugging in for x. That's what this notation means. I have a question for you. Is f of a plus h 1 over a plus 1 plus h? Or is f of a plus h 1 over a plus h plus 1? Which one of these is correct?
The bottom one.
Yeah, very good. The bottom one is correct, right? Are either of these the same as f of a plus f of h?
No.
That's correct. Yeah, Ainsley's correct there. So some of the mistakes I see people make with function notation is trying to distribute this f. So saying f of a plus h is f of a plus f of h. That's not true. All right, that does not work. This is not multiplication, right? This is function composition. We're plugging a plus h into the function f. And similarly, for the same reason, because this is function composition, this is not correct. So if you want to find f of anything, take the formula for f of x and replace x by that thing. So here, since f of x is 1 over x plus 1, f of a plus h is 1 over a plus h plus 1. We just take whatever is in here and we plug it in for x in the formula here. And you want to be careful, sometimes using parentheses if there are any powers or numbers multiplying the x to make sure that, that you follow your order of operations. All right, I've got f of a plus h. This is the correct one. I've got f of a. So now I'm ready to build my difference quotient. The 3 dots oriented like this stand for the word therefore. So therefore, f of a plus h minus f of a all over h is equal to this thing minus this thing, all divided by h. And I remind you that these fraction bars have like implied parentheses. So we have to simplify the top first. How can I write this difference as a single fraction? So looking just at the big numerator, how do I write that big numerator as a single fraction instead of a difference of 2 fractions?
You can add a h to the second fraction, and then so it'd be h over a plus 1 plus h.
Careful, it sounds like you're multiplying by h upstairs, but then
denominator.
adding it downstairs. You're on the right path though, so I think you're thinking the right sort of thing. Jada, what were you gonna say?
I was just saying to make it like, well, basically piggybacking on what she says and make it a common denominator.
Yeah, perfect. And I think that's where you were going, right? Is that we wanted a common denominator. And the way we're going to do that isn't necessarily by adding, but by multiplying. So first, let me draw my big fraction, put the h downstairs. This first guy has 1 over a plus h plus 1, but he doesn't have a factor of a plus 1 downstairs. So I'm going to multiply him by a plus 1 over a plus 1. And then we still have our 1 over a plus h plus 1. Minus, extend my big fraction bar a little bit. So this guy was missing the a plus 1 factor. This guy is missing the a plus h plus 1 factor. So I'm going to multiply him by a plus h plus 1 over a plus h plus 1, like this. And still got his 1 over a plus 1. So this is how we have a common denominator. All right, we multiply top and bottom in any pieces by the factors that they're missing. So I have, if you multiply these fractions here, you'll have a plus 1 over a plus 1 times a plus h plus 1. And then this minus is this minus. Here we'll have a plus h plus 1 divided by a plus h plus 1 times a plus 1. And all this is still over h. Now, if you look at the denominator at this step, this guy's denominator is a plus 1 times a plus h plus 1. And this guy's denominator is a plus 1 times a plus h plus 1. They're just written in the other order, but it's multiplication. Multiplication is commutative. So now they have the same denominator, which means now I can subtract the fractions. And the parentheses that I wrote here are actually pretty important. You want to make sure to distribute this negative sign. So I would write it just as I've written it here. A plus 1 minus parentheses a plus h plus 1 over this common denominator, which is a plus 1 times a plus h plus 1. And then all of that is still being divided by h. And again, implied parentheses upstairs. Sometimes it's nice to actually write them to help you remember what order the division is being done in, because division is not commutative. Questions up to this stage? Okay. I'm going to distribute that negative, combine like terms, and we'll be done with this. Okay. I have a plus 1, and now distributing this negative, I have minus a minus h minus 1. That's being divided by a plus 1 times a plus h plus 1. And all of that is being divided by h. So the positive a and the minus a here, those will go. I've got a plus 1 there and a minus 1, those will go. I'm going to move the page up in about 5 seconds. So combining those like terms, I'm just left with negative h over a plus 1 times a plus h plus 1. And all that is still being divided by h. The last thing we need to do here is kind of simplify the big fraction. The numerator is now fully simplified. There's nothing more I can do with this piece. But I've still got this big fraction with an h downstairs here. So it's like a compound fraction, right? A fraction within a fraction. And the way you simplify those depends on kind of the order, right? The big parentheses out here are important for this. I think everybody probably knows it involves something like flipping and multiplying. What do we flip and what do we multiply?
We multiply 1 over h to the numerator.
Very good, yeah.
H over 1.
So
Don't you flip it?
this piece
Oh.
will stay. And this piece I need to flip and multiply. So my suggestion is to think of the top and bottom as fractions. The bottom is the fraction h over 1, right? H is h over 1 in the same way that 5 is 5 over 1 or 10 is 10 over 1. So I leave the top alone. And I multiply by the reciprocal of the bottom, which is going to be 1 over h. And then you can multiply these fractions straight across. And now you have a common factor of h in the top and bottom. The top is negative h. The bottom is a plus 1 times a plus h plus 1 times h. So you can cancel those guys. When you cancel the negative h and the h, the top becomes negative 1. Downstairs you have now a plus 1 times a plus h plus 1. And that's how these are done. I know it's something of a long problem, so I'd love to hear what you guys are thinking. Is there any step here you want to look at more closely? Okay. So we played around with domains, net change, difference quotients. I don't think I want to beat you guys to death with any more of the 2.1 stuff, especially seeing that you're all fairly comfortable with the examples we've done. So we're ready to move on to 2.2, which is the information you can get from a graph of a function. Now, at a few different portions of this section in the homework, the problems say, use a graphing calculator to graph this function. You can use a graphing calculator or you can use Desmos. I recommend you get comfortable using Desmos because it's a great tool. There's also an app for your phone. It's free. It's awesome. I love it. And I'll use it in class from time to time. We've graphed a few functions already in this class, but I haven't said exactly what the graph of a function is. So let's go ahead and define that. This is the beginning of section 2.2, which is info from graphs of functions. And the definition, the graph of the function f of x is the set of all ordered pairs of the form x comma f of x, where x runs over the domain of the function f. So, take your favorite input, find the output from that input, form an ordered pair, and you've got a point on the graph. I'd be willing to bet everybody knows this, but the converse is useful. So if I give you a point on the graph, I can ask you, what is f of 3? And if you know the point, associated with x equals 3 on the graph, that y value is f of 3. There's some surprisingly subtle things you can do here. Of course, you can make a graph by plotting a table. You can draw a graph by creating a table of values. I'm not going to go back over that. That is stuff that you guys know, and we'll have opportunities to do examples, explicit examples eventually. So let's go ahead and talk about some power functions. We've already talked about piecewise functions here. So graphs of power functions. Here are some graphs that you need to know. The squaring function, f of x equals x squared. This is your classic parabola. Pretty sure everybody knows this guy. F of x equals x cubed. This is a function whose graph has a different kind of symmetry. In quadrant 1, he looks pretty similar. He goes through the point 1, 1 like that guy. But when x is equal to 2, here 2 cubed is actually 8. So he grows a little faster. So in quadrant 1, the shape is quite similar, maybe a little steeper, a little faster growing. But there isn't anything over here in quadrant 2, because when you cube a negative number, you get another negative number. So what you have over here instead is something looking like this. And in general, if you have x raised to an even power, you'll be looking at a shape more or less like this. And x raised to an odd power, you'll be looking at a shape more or less like this. The difference is that as that power gets larger and larger, the kind of piece between -1 and 1 gets more smushed and flat. I'm going to show you, for example, what x to the 4 looks like. Still going to go through 1, 1, but it's going to come down and be like flatter in here. And then outside of this interval, he's going to go up much faster. Same kind of bowl shape, but this is technically not a parabola. It's flatter on the bottom and it's kind of taller outside of that area. And the next odd power here would be like x to the 5. Same sort of thing happens. He gets flattened out between -1 and 1. But then elsewhere, basically the same sort of behavior. Right, so you see how the two down here are kind of smushed versions of the two up here. If you take this guy and sort of sit on him from the top, he'll look like this as his bottom gets smushed out. And if you take this guy and kind of squeeze him in, he'll look kind of like this. Your textbook has a bunch of other graphs from these families, and I'll show you in Desmos what they look like. But first, maybe I'll give you just a second to write these down. And while you're writing these down, I'm going to grab some coffee. Because you're feeling sick, like just to ask if there's something we should do. Okay. All right. So let's take a look at some more graphs like these in Desmos, just for fun. You don't have to put these into your notes, but I want to show them to you. I'll just type y equals. Okay, so here are the two that we looked at, right? In red, you've got x squared. And then in blue, you've got x to the 4. And just like we drew it, the x to the 4 is bowl-shaped again, but flatter on the bottom. If I go up with more even powers, you see that pattern continuing. You start with the nice parabola. And then x to the 4, the blue one here, is a little bit flatter. X to the 6 is a little bit flatter still. And x to the 8 is a little bit flatter still. So that pattern continues with the even powered power functions. And every single one of these goes through these 2 points, 1, 1 and -1, 1. If we do the same thing with the odd powered power functions, as promised, you'll see the same sort of pattern. So here's x cubed in red, and then x to the 5. Same sort of thing, right? Still has that overall S shape, but the blue curve is flatter between -1 and 1. And then as that odd power increases, it's flatter still. So here's x to the 5 and x to the 7 in green. And then here's x to the 9 and x to the 7 with x to the 9 in the purple. So those are your basic power function graphs. Some other things which are power functions are the square root function, the cube root function, and the reciprocal function. it's critical that you remember these because later we're going to be building more complicated functions by shifting these around, stretching them out, flipping them over, that sort of thing. The square root function has a graph that looks like half of a sideways parabola. That's the graph of the square root of x. And you see he goes here through 1, 1 and 4, 2. The cube root of x similar in shape. But he grows a little slower. You got to come all the way out to 8 to get up to 2. And like there was a symmetry with the odd powered power functions, there's a symmetry with the odd root functions too. So this is what the graph of the cube root function looks like. Finally, I'll show you 1 over x and 1 over x squared. All right, here's what the graph of 1 over x looks like. He has some asymptotes. You may have heard that word before. We'll talk about those later. One over x squared in quadrant 1 looks pretty similar to 1 over x, but he kind of sits down on this x-axis here harder. And then he has a different symmetry. Okay. Okay. So some basic graphs, basic shapes that you need to remember. And if you need to flesh any one of these out, of course, you can always make a table of values, right? Make an XY table. You can get as many points as you need and therefore as much detail as you could need. We talked last time about piecewise functions, how to evaluate piecewise functions, and we drew a couple graphs. I want to graph one more piecewise function for you here today. While we're here, I'm going to say something important. So go ahead and put your pencil down for a second, just listen. In WebAssign, there are only so many problems where I can make you draw a graph. Most of the time, the WebAssign problems, you'll have like 4 or 5 graphs that you have to pick the correct one from. When you're working those problems in the homework, you must draw the graphs by hand. If you do not practice drawing those graphs by hand, you will be completely fucked when it comes to the test, because I will make you graph functions by hand on the test. It's happening. If you're going to get through this class, you're going to learn how to graph. It's the single most important thing for Calc 1. The only way to do well on those questions on the exam is to practice them on the homework. And I know that the way WebAssign is set up, it's not the best way to force you to practice them, because it's very easy to just kind of guess and check, or work your way to selecting the correct graph from the 4 or 5 they have you choose from. So please, when you're working those problems in the homework, draw the graph by hand. Then ask which of these graphs that they gave me looks most like my graph, and pick that one. Do not just guess and check. You will be hurting yourself massively by doing that. You must practice graphing by hand. Okay, here we go. We've talked about what piecewise functions are. So let's sketch the graph of, I'll give us a nice piecewise function to play with. X squared if x is less than or equal to 1. And 2x plus 1 if x is strictly greater than 1. Now I think, was it maybe Jada yesterday who said, are we just like putting graphs together for these piecewise functions? Is that what we're doing? I apologize if it wasn't you, Jada. But yeah, the answer to that question was yes. Yes, the way we make a graph of a piecewise function. Okay, good. I'm glad I remembered right. Is to take the graphs of each of the pieces, kind of chop them up, and then glue them together. So my 2 pieces here are x squared and 2x plus 1. We know what the graph of x squared looks like. That's one of the basic graphs we just talked about. And if I look at the restriction here, this says my function plays like x squared if x is less than or equal to 1. So I want to make sure I draw 1 on here. All right, so there's the point on my graph associated with x equals 1. My other piece is y equals 2x plus 1. So let's draw that graph. That's a line with slope 2 and y-intercept 1. So that piece looks like this. And again, I'm going to kind of emphasize the point here at x equals 1. Now, the way I'm going to kind of cut these up and glue them together to get the graph of my piecewise function is to take the 2x plus 1 graph and throw away any part that doesn't have x being greater than 1. So I'm going to throw away, here's x equals 1. The x's which are greater than 1 are the x's to the right of 1 on the number line. So I'm going to throw away any part of that graph that's associated with stuff to the left of 1. In other words, I'm going to retain only this part, because that's the part that's associated with the x's which are greater than 1. And similarly, when I look at my x squared graph, I only want to retain the portion of the graph associated with x's which are less than or equal to 1, which is this part of the graph, because those x's are the x's that are to the left of 1. So these are the x's which are less than or equal to 1. And so the portion of the graph I'm going to hold on to here is the portion of the graph associated with those x values. So now I take the highlighter portion here and the highlighter portion here, and I glue those pieces together, and that will give me the graph of my piecewise function. The y value at this point is 1, right? This is 1, 1, because we're along the graph of x squared. 1, 1. So there's the part of the piecewise graph that I'm going to hold on to from my x squared piece. The y value here at x equals 1 is 3, right? Because if you plug x equals 1 into this, you get 2 times 1 plus 1 is 3. So we come up here to 3, and we're going to graph this piece. Now here, notice I only want the x's which are strictly bigger than 1. I'm not actually including the point that comes from x equals 1 itself. And if I did that down here, if I included that point, then this wouldn't be a function anymore. This would fail the vertical line test at that point. There would be 2 outputs associated with that input, which is not allowed. So the graph we have down here is the graph of f of x. This is my answer. That's how you graph a piecewise function. Graph each of the pieces, then throw away the parts you don't need, glue the parts you do need together according to the rules specified here. Any questions on this example? Okay. One more important example of piecewise function. The absolute value function is a piecewise function. You want to take the absolute value of some number? Great. If that number is greater than or equal to 0, leave it alone. It's its own absolute value, like the absolute value of 5 is 5, the absolute value of 7 is 7. If that number is negative, if that number is less than 0, then you're going to multiply by another negative to turn it positive. This is the algebra definition of absolute value. And following the exact same rules we just used, you could draw its graph. Here's the graph y equals x. It would continue like this, but I only want the part where x is greater than or equal to 0. Here's the graph y equals negative x. It would continue like this, but I only want the part where x is less than 0. This is the graph y equals absolute value of x. Okay. Okay. There are a few things I need to describe to you before we can kind of charge forwards much further. We've already talked about domains and ranges. I want to talk about solving equations and inequalities graphically, but I don't know if we'll have time. So let me go ahead and define increasing, decreasing mins and maxes. And then if there's time, we'll talk about the inequalities. What does it mean to say a function is increasing? What does it mean to say a function is decreasing? Okay. So we say that a function f of x is increasing on the open interval AB if the graph of f of x rises as we go left to right along that interval AB. And if you want the definition of decreasing, you just swap rises with falls. So if you're going up as you go left to right, that's increasing. If you're going down as you go left to right, that's decreasing. The real important thing here is that we always use open intervals of x values to describe increasing, decreasing. I can't say this enough. No matter how many times I say it, I'm sure there will be some mistakes made. There always are. If I ask you where is a function increasing or decreasing, your answer should